Last problem. So for this function, let's notice that the domain is everything except 0. I guess we'll start by studying what happens at 0. As x goes to 0 from the right, this goes to 0, this goes to infinity. So our function is shooting up to infinity. As x goes to 0 from the left, again, this part just goes to 0, but this part actually goes to minus infinity, and so the whole thing goes to minus infinity. And then you can check that the limit as x goes to plus or minus infinity of h of x, both of those shoot up to infinity. That's actually going to be interesting to see on the graph. When x gets big, positive or negative, this part goes to 0, leaving you with this. So your graph is going to actually look like x squared for, let's say, for large x. And so we'll see that when we go to graph it. All right, so let's take the first derivative. So h prime of x is 2x minus 1 over x squared. I want to figure out where this is 0, so it's behoovious to me to go ahead and combine this as 2x cubed minus 1 over x squared. And so that's h prime. And I want to mark on my number line not only where is it 0, right? It's 0 at 1 over the cube root of 2. That's an important number. But it's also 0. It's also undefined at 0. And so we want to go through now and carefully label our number line. And so when I plug in something bigger than this interesting 1 over cube root of 2, I'm going to get positive. In the middle, I'll get negative. But also on the other side of 0, I'm also going to get negative. So this function, my original function, is not defined at 0, but on both sides of it, I'm decreasing. We should probably mention that 1 over cube root of 2 is roughly 0.7937. And so when you plug that in, h of 1 over the cube root of 2 is roughly 1.89. And so I'll need that information when I want to graph it. Finally, let's take the second derivative. So h double prime of x, I get 2 plus 2 over x cubed. I want to figure out where this is 0. So if I set that up and solve, I'm actually going to come up with x equals negative 1. You can kind of see this. If you plug in negative 1, it's clear that it's a 0. And so interesting that that happens to be our x-intercept. Doesn't happen all that often, but there we go. And when I look at negative 1, and I want to, let's also, I want to plot negative 1, but I also want to plot where the second derivative is undefined. See, it's undefined at 0 as well, and it might change sign there. That's really important that we catch that. The second derivative, or the first derivative, or the function can change their sign anywhere they're undefined. It's like you crash into that undefined place, and who knows what comes out on the other side. So I do want to go ahead and plot 0, even though the only potential for an inflection point is at negative 1. So let's see, when I plug something bigger than 0 into h double prime, it's pretty clear that it's going to be positive. Let's plug in minus a half. When I plug in minus a half, I get 2 plus 2 over minus a half squared. It's going to flip up. This thing is going to be negative now. And then when I go in and I plug in, I don't know, negative 2, it's going to go back to being positive because the small number, the large number in the x cubed downstairs is going to make this small, and the negative will be swallowed up by the plus 2. So that's the number line for h double prime of x. So I'm good to go now. I guess I should point out to you that negative 1 is an intercept, so I already know that h of negative 1 equals 0, so I've got that inflection point. So let's see if we can graph it. At negative 1, we're 0. We've got that. I am going to go ahead and actually sketch, I'm going to try to sketch x squared, and it's going to look something like that. And like I said earlier in the video, I know that my function is going to follow x squared when x starts to get large. So now I've got my -1 graphed, and then I've also got this 1 over cube root of 2 is worth graphing as well. So let's see, that was, the point here is 0.79 comma 1.89. So let's just put that roughly here. 1.89 is roughly somewhere, if this is 1, will be somewhere, I'm sorry, I'm struggling to keep track of all the dots here. Somewhere here, we'll say. This is my local min. I know that I'm going to be increasing and following out x squared. So again, you might be tempted to draw it, oh, you just shoot off to infinity, but you can actually be more precise. You're going to look like x squared for x large. So not in here, but as you go farther out, you're going to be looking more and more and more like x squared. All right, and then what do we see? Looking back at the first derivative, I'm decreasing between 0 and this local min. I'm just going to decrease right down to this local min, and then I want to check. I should be concave up everywhere from 0 on, and I am. That's good. Okay, this side is a little weird. You know you're going to go from the x-intercept, and you're going to shoot down to minus infinity, because we said the limit as x goes to 0 from the left is minus infinity. Okay, then you've got to switch concavity. So I've got an inflection point here, and I'm going to come up. Again, I look nothing like x squared here. But as x starts to get larger, I'm going to look more and more and more like x squared, and I'm going to follow that graph of x squared out and look something like that. So here's a graph of h of x. All right, you've got everything you need to do the homework problems from 4.4.